In this operational amplifier circuit, I am trying to find the output voltage versus the input voltage. As my transfer function, I just have these two resistors here, and I have a ground connection at the bottom. So ultimately, I want to find this transfer function G, that is Eout over Ei. Okay, with an op-amp circuit, I'm going to choose not to use the voltage loops or trying to use the Kirchhoff laws, but I think it's going to typically be easier to be using the nodal voltages or finding the voltage drop between neighboring nodes to develop equations that way. So for my diagram, I'm going to make my own version of this circuit that I'm going to be able to mark up easier. All right, so I have this node is going to be connected to ground. I'll have a node over here, and this is going to be my Ei. This goes through resistor R1. It's going to come to a node. I have the op amp. I have the negative terminal and the positive terminal, which don't matter too much what the difference is for our purposes, but coming down there. I have the output from the op amp, and then that output is connected, and that's EO is the gap, and then it's connected to that bottom. And then I have one more connection point here. I'm going through this R2 resistor and coming down to this point where I have another node. So with these circuits, I find it helpful to label at each of these nodes I created what the voltage is. If I know it, or if I don't, I can create a variable that I'll be able to solve and put into equations. So let's start labeling some of these voltages. Well, ground is going to be 0 volts. So I want to label that as 0, and I'll put these down here. That's 0. Okay, everything connected just by wire to that node will have the same voltage because we are going to be using these perfect wires that have no resistance in them. So everything directly connected also has to have the same voltage. So if I go over to this node, that also has to be 0 volts, and this node. And it's also connected to one more node up here, which is 0. We can see a couple other nodes that we can label. So if in the bottom left, that is 0 volts, and then I am crossing a voltage of Ei, that means in the top left here, that must be Ei. Now if the bottom were not 0, I could not label this simply as Ei. I would need to figure out what it is, but here that must be Ei. In the bottom right, we have 0, and we're going across EO or Eout, which means that the voltage at that top right node must be Eout for the voltage difference between them to be E0. And it's connected by just a wire to this node, so that must also be E0. So actually at this point, I've been able to label all but one node so far. So let's see how we can either name that or do we know what the voltage of that is. Well, it's not Eout because there is a resistor between the node and the EO on the right. It's not Ei because there's R1 between the left node Ei and the node that I am looking at. But because I have this ideal op amp, we know that the voltage going into the op amp must be the same. So I know that going into that positive terminal is 0 because it's attached to the ground. So if this is an ideal op amp, then this top node here going into the negative terminal has to be 0 as well. So now every node I was able to label in this example with just a 0 because it was connected to the ground or because of the ideal op amp, or Ei or EO because I know the voltage drop between the Ei and the EO goes to 0. Right, so actually I was able to label everything, so now I can move on and look at currents. All right, so I'm going to start by looking at this left node Ei to 0 that goes across R1. There's going to be some current across there. I'm going to call that I. So this is not a loop. This is just the direction that the electrons are flowing. I'm going to say as I go across R1, I is going left to right in the positive direction. Now, every time I get to a node, if it splits, I'm going to have to split that current. However, I know in the ideal op amp that the current going into the inputs is going to be 0. So when I'm now at this 0 voltage node and the current splits, well, it splits, but one of them is 0, and then the other splits in this direction. Since one is 0 using Kirchhoff's current law, it must be true that the output is also I. So I is coming into that node, and a total of I is going out of that node, but it's I plus 0. Right? And then that current is going to flow through. It's going to continue. This is still I over here. And actually, that's all I really need to label. I guess I'll put in the rest of the I's just to make it clear what's happening. But now let's see if we actually have enough information to start developing the equations we're going to need to solve for our desired transfer function, the Eout over Ei. Right, so let's look at equations that we are able to develop. Now there's a lot of equations that we might be able to write here. There's a collection that might be more efficient, that we can get the transfer function we want with maybe a single equation, or 2 or 3. We could write maybe 6 equations before we have enough information to solve what we want. I'm going to present one collection of equations that we could use to get our desired transfer function. So using nodal voltages, let's start with this pair first. I'm going to look at going from this node Ei to this node of 0. So I know that the voltage drop, this is going to be my equation 1, I'm going to go from the end point back to the start point. So 0 minus Ei, that is the voltage drop, is equal to, now I'm going across just one element here, R1. And when I go across an element, I know it's, since I'm going left to right, that that is going to be negative times the, well, it's a resistor, so it's the current times the resistance. So negative I times R1. Now I can clean this up a little bit. I have this 0 minus Ei is going to be negative Ei, but I can drop that negative sign, and I know that Ei equals IR1 is the how I can rewrite this first equation here. And if I look at my output and my input, potentially multiple outputs, in this equation my one output is I, and I have an input which is Ei. So I don't have enough yet because that current I didn't really need to solve for, but the way I'm generating these equations, I could find it along the way if I wanted to. We'll see that I'll actually do this one by hand rather than using Mathematica, but we could use Mathematica and also find then I over Ei, that transfer function. We could actually do that right now if we wanted, but I'm going to hold off on that. So 2, I'm going to now look at a second set of nodes and look at the voltage drop between them. So let me use here, for this one, I'm going to start where I ended the last one at that node, and I am going to go to this EO node over here. So to get from that one, the start node to the end node, I am going to go across R2. Right, so let's see what happens. So let's see what's the voltage drop as I go end point minus start point. Well, I'm ending at EO, but I'm starting at, well, 0. So end point minus start point, my end voltage is Eout, my start is 0. And I'm going across one element here, R2. So I'm going to have a drop of the current, which is actually also I, times the resistance, which is R2. And I can rewrite this as 2a, that 0 is going to go away, so I'm left with Eout equals negative I times R2. Looking at the outputs, I've now added an output Eout, and I still have my one input Ei. So if I look at 1a and 2a, I have Ei, I have Eout. I can get to the transfer function that I want, because I want Eout over Ei. So either use Mathematica, or this one is easy enough to do by hand. I'm going to take equation 2a, and I'm going to divide it by equation 1a. So why am I doing this? Well, this lets me have here Eout equals negative IR2 over 1A is EI equals IR1. Now, if I clean this up a little bit, rewrite this a little, get rid of that, I have this. So I divide the left-hand sides, I get Eout over EI. Divide the right-hand side, I get negative IR2 over IR1. Okay, well actually the reason I did this and the reason that by hand this is not too bad is that this is giving me then the transfer function I wanted, Eout over EI, that is G. And the nice thing here is that the i's are actually going to cancel each other out. And I'll be left with negative R2 over R1. And actually I'm done at that point because I have my transfer function. It turned out to be negative R2 over R1, and that's the entire transfer function. Now notice I have R1 and R2 must be positive values. Resistances can only be positive, but we have a negative on the outside. That indicates that this is an inverting circuit. So if the input voltage is positive, the output voltage will be negative, and vice versa is also going to be true. We have our final transfer function. Let's review how we got here. We had a circuit, 2 resistors, but we had this op amp. So what I wanted to do was make my own version of this diagram. The first thing I did was try to label as many of the nodal voltages as possible that I could identify. Well, the easiest place to start was anything attached to the ground is going to have 0 volts. So I have directly at the ground, and then any wire that directly connects to it must also be 0 volts. So the left node, the right bottom node, and then I can come up here and say that that's 0. This then let me go on to identify the nodal voltages across these gaps. Since this is 0 and I have a voltage difference of EI, that means that this top node must be EI. Again, because that's 0, I can directly say that this then is EI. Same idea here, Eout on top, 0 at the bottom because the voltage difference is Eout or EO. This is also EO the way I drew it because it's connected with a straight wire. The last nodal voltage I was able to identify by using the ideal op amp, that the voltages at the negative and the positive input terminals must be equal. So since I knew that the positive terminal, it was 0 from being connected to the ground, then the final nodal voltage also had to be 0. So nodal voltages identified. Now I can start drawing some of my currents. So I just started over here with EI. I'm assuming I is going to the right as I go to the node with 0 voltage on it. Then potentially it should split because I have 1 going in, 2 coming out. Because it's an ideal op amp, the current going into the input terminals must be 0. So the I coming in splits into 0 going out and I going out, because due to Kirchhoff current law, the current going into the node must equal the current coming out. So I goes in, I must come out. That goes through R2 and comes back down to that node, and that was enough information actually to develop the equations we needed. I chose to do this one just using node-to-node voltage drops. So I use the EI and the 0 as 1 voltage drop. So I always do the end node minus the start node. Again, looking at the direction of the current to tell me which is the end and which is the start. So the end point is 0 minus EI. If I go along the direction of that current, it is negative I times R1 because I'm going from the input current to where the current comes out. So negative I times R1. That simplified down a little bit. The negatives canceled, so it was EI equals IR1. The second equation I used was the node-to-node voltage drop from this 0 node to this Eout node, which crossed over R2. So again, end point minus start point, Eout minus 0, equals then the voltage drop. Well, we know for a resistor, it's going to then be the negative current times resistance, I times R2. At this point, we had enough equations for the number of outputs we identified. We could use Mathematica. This one, though, by hand was easy enough to get Eout over EI by just dividing our 2 equations, the 2a over the 1a, and gave us the transfer function that we were looking for. And in the end, we got negative R2 over R1. Since it's always going to be a negative result, that tells us we have an inverting circuit that is going to reverse the polarity of the input by the time it gets to the output.